Hi, my name is Anders Holm. I'm a professor at the Faculty of Social Sciences at the Department of Sociology. In this lecture, you'll get an insight into what we more precisely mean by causal effects and how causal effects are measured. Often data just give you correlations. There's a positive correlation between substance abuse and criminal behavior. There's a negative correlation between smoking and longevity, and so on. But does that mean that it's the use of substances that lead to criminal behavior, or is there a third factor, for instance, ability to postpone desirable outcomes, that determines both substance abuse as well as criminal behavior? In this course, we'll learn how to distinguish between statistical and causal relations using quantitative data, and also when it's not possible. Causal effects may warrant decisions on what to do. Statistical relationships cannot guide decisions. Much social science research uses very complicated theory to explain very complicated mechanisms. This is not the aim when we empirically try to establish causal relations between different variables. We ask very simple questions, and the answer is often very simple. Do class size influence math achievement? Do gender affect promotions? Do travel time affect journey frequency? Or do teacher education influence students' performance? Do class size management skills affect student learning? Or do corporal punishment cause depression? We'll not ask what causes why, unemployment, learning, promotion, wages, etc., but rather, does a particular X training program for unemployed, class size, gender have an effect on Y? So we do not explain all the variation in Y, only the bit that might be attributable to X. Furthermore, we are not satisfied with multiple interpretations of research findings. We want to test whether one hypothesis is supported by evidence. This hypothesis may warrant further investigation, deeper analysis, etc., but we would like to apply a research design that is in principle able to either accept or reject a given research hypothesis. More complicated questions concerning poverty, social class, substance abuse, and learning are more fluffy in the sense that they are more difficult to measure. Research questions on these topics could be: do poverty affect educational achievement? Do social origin cause social class destination? Do substance abuse cause criminal behavior? Do innate intelligence influence learning? Why more complicated? Well, while class size and math achievement are relatively straightforward to measure, you count the number of students in the class and you give a student a standardized math test. Things like social class and criminal behavior do not have a unique and simple measure. Researchers even disagree as to whether there exists such a thing as innate ability. So while some questions seem very natural to ask because they seem part of an everyday discussion, no straightforward and generally agreed measurements are available. So the choice of measurement is a discussion in itself. So quite often, precise research questions require operationalization of more abstract terms into something that's actually measurable, something that materializes in the real world, as for example in the case of poverty, where you can use low annual income as measurement, social class, where you can use an agreed class scheme, or substance abuse, where you can use alcohol consumption, soft drugs consumption, or hard drug consumption, or learning, where you can use grades and test scores as outcomes. As an example, consider the relationship between social class origin, parents' class, and social class destination, children's class destination. We'll use data from a UK cohort from the children born in the mid-1950s. The table shows the row frequency of ending up in one of the three social classes: the service class, the middle class, and the working class. Each row in the table reflects parents with a different social class, the child's class origin. For instance, if the parents belong to the service class, almost 60% of the children end up in that same class, whereas less than 9% ends up in the working class. Conversely, if the parents belong to the working class, only a third ends up in the service class, whereas 20% ends up in the working class. So while there's a far from deterministic relationship between class origin and destination, the risk of ending up in a particular class seems to depend crucially on class origin. The question, however, is whether this is a causal relationship. To answer the questions as to whether the relationship between class origin and class destination is causal, we have to think more carefully about what we mean by causal. There are many definitions, but researchers seem to narrow down on the concept of counterfactuals, or what if. The idea here is that if someone manipulates X, then Y changes. If I turn the switch and the light goes on, then I tend to believe that turning the switch causes the light to go on. If I replicate this many times and the light goes on every time, I would tend to believe that the relationship is actually deterministic. If the light tends to go on more often when I turn the switch on than when I turn it off, I would tend to think that the relation still might be causal, but that other factors that I do not control matters too. Now what if the light sometimes goes on if I turn the switch off? So in the example, we are interested in whether manipulating class origin changes class destination or whether the relationship is just spurious, being caused by other stuff. The arrows in the figure indicate causal relationships. So from the figure, we see that there is a causal relationship between class origin and class destination, but there are also a causal relationship between class origin and parental mental ability, and the arrow indicates that parental mental ability causes parental class origin and not the other way around. Parental mental ability also causes class destination. Parents with better mental ability get children with better mental ability, and children with better mental ability reach higher class destinations. Now imagine that there's no direct causal relationship between class origin and class destination, but that parental mental ability causes both parental class origin, and the class destination. In this case, switching class origin on and off does not change class destination, but switching parental mental ability on and off causes changes in both class origin and class destination. The crucial message is that both causal mechanisms can generate the table of the relationship between class origin and class destination, even though they have completely different interpretations. The previous exposition has somewhat mixed causal mechanisms and our ability to detect causal mechanisms. Causal mechanisms are there whether we can infer them or not, but we use data and statistical methods to detect them. We therefore review some of the workhorses in analyzing and inferring relationships between variables, the linear regression model. We assume some basic familiarity with the statistics and regression models, but we have reviewed the linear regression model with one or several independent variables and emphasize the concept of statistical control in terms of a regression analysis. In regression models, the variables that we may think causes something is usually called the independent, the explanatory, or the exogenous variable and is denoted x, while the variable being caused by another variable is usually called the dependent or the endogenous variable and is denoted y. In the figure, we see two types of relationships between the dependent and the independent variable, a linear relationship and a nonlinear relationship. While both are very relevant, we'll confine ourselves to study linear relationships between x and y. This is only for exposition. Nonlinear models tend to be much more complicated. The linear relationship is captured by a constant a that measures the level of y when the value of x is 0, and another constant usually referred to as the slope b that measures the change in y for 1 unit change in x. If, for instance, x is class size and y is test score results, then b measures how much test scores are affected by one extra student in the class. Here we would not expect that b is negative. More students yield lower test scores. Let's now take some data to the regression model. Data is shown as dots in the figure. Each dot is a pair of numbers that designate the corresponding x and y values. So if x is income measured in US dollars and y is a child as an adult income also measured in US dollars, then the dot in the figure is a corresponding income of a parent and a child. As can be seen from the figure, there's not a deterministic relationship between income of parent and child. At best, there's a trend. The larger the value of the parent income, the larger the value of the child income. So the slope b is positive. One reason the non-deterministic relationship between parent and child income could be that other factors than parent's income is related to child income. For instance, parental education, parental wealth, parental mental ability, and so forth. Anyway, we define a residual term as a difference between the observed child income and what would be implied if the child income followed the linear relationship between the parent and the child income. The lower error, the better the observed data point fits the simple linear model. In fact, A and B are chosen as to make the sum of errors as small as possible. Given that we want to minimize the error, how would we estimate B, the slope? The slope is important because it indicates how y varies with x. If the slope is 0, changes in y are not related to the change in x. It turns out there is a formula for the slope. the covariance between x and y divided by the variance of x. Hence the slope is a measure of linear association between x and y, but the measure is sensitive to both the scale of y and x. The slope is related to, but not identical to, the correlation between x and y. If we can calculate the slope from a sample of data, we might also be interested in the precision of this estimate. That is given by the next equation. It says that the precision or standard error of the slope is proportional to the residual sums of squares, RSS, and inverse proportional to the number of observations, n. This makes sense. The worse the model fits the data, the larger the residual sums of squares, the RSS, and the smaller the standard error of the slope. Also, the more observations, the smaller standard error of the slope. Perhaps a little less intuitive, the larger the variance of x, the smaller the standard error of the slope. But this does in fact make sense. The more x varies, the better we are able to judge the slope. We can further assess the fit of the model by comparing the residual sums of squares, RSS, to the total sums of squares, TSS. The difference is the variation in y explained by x. Hence model fit, or R squared, is a percentage of the variation in y that is explained by x. In the next lecture, we'll expand the regression model to allow for several independent variables, and I'll show the logic of statistical control, i.e. what happens to the effect of one independent variable when we control for other variables. Thank you for your attention, and looking forward to see you next time.